Hello, everyone. Good afternoon to all the participants. Welcome to Brain Quantum Physics Colloquiums. My name is Gagus. I'm researcher at the Research Center for Quantum Physics, a national research and innovation agency of Indonesia. And today I'm serving as a moderator for today's colloquiums. I would like to inform you that we organize our quantum physics colloquium 2 times every month. So we invite speakers from our research center and also guest speaker from other institutions. So for this year's, this is our second colloquium, and we are pleased to have Dr. Yap today as our guest speaker from UTM, University Teknologi Malaysia. And Dr. Yap will speak about introduction to superconducting quantum computers, and this talk will introduce about what is quantum computer and how to build one, how one can control the qubit using quantum gates, how to create this gate, and also the speaker will also share recent research finding on variational quantum eigensolver for nuclear pairing calculation using quantum simulators. So it's my pleasure to welcome Dr. Yap today. Hello, Yap.
Hello, hi.
Hello.
Thank you for having
How
me.
are you today?
I'm good. I'm good.
Okay, thank you so much for being with us today. Yep. And please feel free to share your screen first.
All right. Meanwhile, would you prefer if I explain this in Bahasa Melayu or?
I think English is okay, both of them is okay. Uh,
Uh,
yes,
sure.
English is also okay. And before we started, please allow me to briefly introduce our speaker today. Dr. Yap obtained his Ph.D. in science, specifically about electron spin resonance quantum computing at Osaka University, Japan. And he is currently a senior lecturer at the Faculty of Science, UTM. And he is also an invited researcher with Center for Quantum Technology Singapore and associate professor at the Graduate School of Engineering Science, Japan. So together with these groups, Dr. Yap working on superconducting quantum computers, and his latest position is in the Chief Technical Officers and co-founder for AK Solot,
Axolotl.
NTU Solotot, NTU, and also a US startup in building quantum computers. So with that, Dr. Yap, are you ready for your presentations today? So if so, you have 1 hour for your presentation and 30 minutes for your question and answer sessions. And please be informed to all the participants today. If you have any question during presentation, please post your question in the Zoom chats. And if you want to ask directly to Dr. Yap later after finish his presentation. So if so, Dr. Yap, the floor is yours.
Thank you very much, Douglas, and thank you to everyone for having me here today. I'm happy, and it's a privilege to be able to share some of my experiences, and hopefully it will be useful to you. So the picture here is actually the work that is done in Singapore with the Center of Quantum Technologies in NTU. There's also another one in NUS. So most of my talk here will be, if there's any pictures, it's actually the work done in Singapore CQT. So our group in Singapore is led by Prof. Rainer, and there's a lot of postdocs as well. And Dr. Rangga is one of the postdocs, the research fellows in the group as well. He's from Indonesia, and there's, as you can see, it's very multinational, different nationalities. So Malaysia, our PI is from Germany, Singaporean, Vietnam, French, right, India. So what we are doing is, so forgive me if I start from a little bit basic, because I'm not too sure who's in the audience today. So quantum physics is something that some properties that you can actually see when things are going down to very small scale. So this can be anything. It can be distances, so length, from kilometers go down to nanometers and picometers, then you start to see quantum mechanic properties or even temperatures. So if you start with boiling temperature for water, then you cool down, you get the freezing point of ice. And if we cool down, we get 77 Kelvin. So that's the liquid nitrogen temperature. And then if you cool down some more, you get the liquid temperature for the liquid helium, right? And right at the extreme end is at 0 Kelvin, where we have the absolute temperature. So nothing can reach that temperature. In between here, let me fill up the gap for you. For the empty outer space, the temperature is roughly about 2.7 Kelvin. So it's much colder than liquid helium. And if you cool down a little bit more, you reach superfluid helium. So that's about 2.17 Kelvin. And something interesting actually happens here. So liquid helium, as you can imagine, it's liquid. And if you use a cup to put it like this picture here, you put it into a cup. Typically, normal water, it will just stay inside, tak gerak mana-mana. But when you have superfluidity, there is no viscosity whatsoever. The liquid helium, superfluid helium, can crawl the top, naik atas, and then go down by itself. So if you not minum kopi or something from the cup, if it's superfluid, the coffee will come out of the cup, so you don't get to drink much. On the other hand, if you have an empty cup and you put it into superfluid helium, the helium will flow up and into the cup. So these are not things that you will normally expect in higher temperatures. And at slightly lower, more temperature is where we use a device, a peti sejuk, a refrigerator, called helium-3 and helium-4 dilution refrigerator. And this can go down to 10 millikelvin. So that's very, very cold. And it's one of the only device capable of cooling bulk material. So if you have a mouse, for example, and you want to cool it down to 10 millikelvin, you can do that. But of course, typical mouse won't operate at that temperature. You have some ICs chip, you can actually cool it down. So people use this temperature to study certain effects, and we use it for quantum computation. So the picture here is the first time in my life to reach millikelvin temperature. It was in Japan a long time ago. It's not 10 millikelvin, but it's about 60 millikelvin. So that was the first time we went to what we call the base temperature. So millikelvin range was successful, and I was very happy at the time. So that's something that I capture in my life. And if you want to go cooler than 10 millikelvin, you can do that, but it's not bulk material. So for example, you use laser cooling, you have atomic clouds, and then you cool them using mods. And you can go down to micro Kelvin, or sometimes I believe they use hertz to represent the frequency of the temperature. And this is what it looks like. So this was the older setup that I was using. Older as in not too old, but it's a smaller system. And there's a bigger system right here. So that's Ranga here, and these are some postdocs as well. And this is how it looks like. So the reason why I'm showing this is you can see different stages of the insulation. So although there are different machines, but the one outermost is either blue, white, or some color. Recently I saw some pink one as well, pink color. Then when you open the first layer, you get this kind of like some fall. So I was told that this is the same material they use for like satellites in outer space as well. Then after that, you start seeing this gold color. So you have a lot of layers of protection. And this is to prevent heat from entering to the coolest area, because there's actually different stages. So here's is another view of it from bottom down. So each of that shield is connected to one of these plates, and these plates have different temperatures. So we will see this a little bit later. And the question is, why do we want to use quantum computers? Why do we need them? So it's about processing information, and it really depends on what you want to process. So for example, you have to do some simple calculation, like here we can't do it mentally, we need a calculator. But if you want to do some sort of simulation, for example, this is FDTD simulation or FEM simulation, you start using HPCs or supercomputers. So I had this situation where I had to do some simulation last time. A single run took 1 week. And when the result is not good, then I have to change something, run it again, and then wait another week. So that was actually taking up a lot of time during my PhD study. You go up higher when you have to simulate atoms. Although it's just a few atoms, this becomes very difficult. If you have to simulate, like I think 10 atoms or something, you already need a very strong system. And it's even worse if you want to do a molecular simulation of drugs. So there's one paper that I found. It says that if you have to do biomolecular simulation, it would take about 1 month running non-stop on a dedicated supercomputers with 3,000 cores. So I'm not of classical supercomputers, but this is actually, well, I believe it's quite a big system. And that's just one run. So imagine if you want to change some molecule or you want to just do some small changes, that would take another 1 more month. And what I heard, for example, recently is the production of insulin. So from human insulin to something they call modern insulin, that took about 20 years just to tweak, to change some parts of the molecule. So imagine 20 years of that compared to what we can do with quantum computers. So here's an example. Google AI, in 2019, they did one demonstration where they had 10,000 years versus 200 seconds. And more recently, the end of last year, was the announcement of from Google for their Willow chip, where they said it's comparable to septrillion years versus I think a few minutes. So that's how fast quantum computer can process information as compared to classical. And the picture here's the two quantum computers. So one is in Osaka, QIQB. That's where I'm affiliated to as well. And the one on the purple color, the one with the casing removed, that's in Singapore. So just to go through the basics. So classical information, why is it slow and why is quantum fast? So we use something called that bits, right? And these bits, the problem with this is that they can only store one value at a single time, which means that if you want to process them, you have to process this, finish this, delete it, and then replace this value. Process it again, delete it, and then replace it again. So it's sequential. And this is a big problem when it comes to lots of simultaneous calculation. So for example, either simultaneous or very long calculations, not single calculations, but many separate calculations. So for example, factorization. You want to factorize a number. You can do that in parallel, many different cores to calculate, but it takes a very long time because you have to do it ultimately sequential. So this is the analogy to it. So if you have a maze, you have to try out one by one. And you hit a dead end, then you start back from the beginning. You hit a dead end, you start back from the beginning. So this actually takes a lot of time. And to speed this up, that is why we have been, using single core, dual core, quad core, 8 cores, 16 cores, then HPCs, and then supercomputers. And also like GPU, there's a lot of cores inside. So all for the purpose of processing information in parallel. So parallel computing. Quantum processing, quantum information processing, they store information using bits. So this uses energy levels. So you see this 0 and 1 notation. And it's similar, sort of like the same with the classical 0 and 1, but the thing is you can store them all at the same time. And when you process them, you process all of them at the same time. So like just now, if you have 3 bits, you have 8 combinations, you have to do one by one, 8 times. Here, you have all 8 at the same time, you process it once. So you have to change this value, you only process it once, compared to just now, you have to do 8 times, right? So this is how you represent it in a equation. And this becomes fast, large, extremely large when you have, say, 200 qubits or 500 qubits. I think about 100 or 500 qubits, the number of combination for this exceeds the number of atoms in the universe. So that's really a big number that we can't imagine. And because it is all processed, it stores all the information together and you process it at the same time. So it is true parallel computing by nature. The property, the sifat dah memang parallel. So when you process all of them, it's like the maze back, you go through all of this at the same time. So that's why quantum computers are very powerful. And if you are going to do something like factorization, you can try a lot of combinations and solve them much faster. So before going into all the more like technical stuff, let's just see what we can do with quantum computers. So here are some possibilities. So you can use them to design new materials. And new materials, I'm not talking like kayu, besi, or kaca, but more advanced material like solar cells. You want better, more efficient, cheaper solar cells, better batteries. All of us want to charge our phone 1 hour and then let it last for 1 month, for example. So, and then the batteries now use lithium. When they pecah, then they catch fire very violently. So maybe you want to design something that is more stable or doesn't use lithium, for example. Those, to do it in the lab, takes a long time. Doing it on a computer, a quantum computer, that will save a lot of time, a lot of trials. You can narrow that down into some chemicals that you think is promising and then go to the lab. That's the same for vaccines and drugs. So we went through COVID. At that time, it was a concentrated effort in the world. Everybody rushed to create the vaccine together. That's the first big worldwide effort. Now imagine if we have quantum computers, you can cut that down significantly and just do it in the lab, in the quantum computer, and narrow down the promising vaccines and try them out in the lab, right? Next is the production of chemicals. We use chemicals everywhere. For example, in agriculture, you use ammonia for plants, and the production of ammonia, baja, has always been the same for the last 100 years. Suhu tinggi, tekanan tinggi, it's expensive. Problem is, from what I heard, you want to use catalyst, but the catalyst is some expensive catalyst. What we want is something cheap, a cheaper catalyst, so that you can actually produce ammonia for agriculture at a much lower cost, lower price. So that can contribute to, solving starvation and whatnot. And quantum computer can help to go through, design different chemicals that may perform their function as a catalyst. Other applications include climate models, more accurate climate models. Sekarang kat hujan, kat Malaysia, hujan every time, and then we have banjir here, banjir there. So having quantum computers may help, to predict and to prepare for that. And also, not forgetting, there's a lot of AI applications now and machine learning, and quantum AI is basically the next generation of AI. Then there's also quantum communication, where we have cryptography based on quantum effects. So that's quantum key distribution, for example, and also for quantum sensing and quantum metrology. And this is used for the next generation of sensors for, let's say, medical imaging and diagnosis. So sometimes people ask, you have all of these examples, but are there any real world examples? So for quantum computers, setakat ni belum lagi ada apa-apa use cases. When people want to see use cases, sometimes they want to see what we call the quantum advantage, something that can exceed classical computers. We have not reached that level yet. There are some demonstration of using quantum computers to calculate, but they are not better than classical supercomputers. But what we do have is, for example, quantum sensing and quantum computing. So MRI, magnetic resonance imaging, is one of the top imaging techniques. And it's not cheap to go for this kind of imaging. And this technology is the same technology that is used to build NMR quantum computers. Exactly the same principle, exactly the same methods. They both use radio frequency pulses. They both use magnetic field. That's why you cannot bring in metal, because there's actually a big magnetic field there. So all of them are based on the same technology. So much so that when a family member of mine went for some imaging, I can sit next to the operator and talk to him about what pulses he has used, what Ramsey's sequence, what's a T1, T2, different background, but basically boleh bual lah. So this is something that you see it being used today. Another example is GPS. All GPS uses atomic clocks, the satellites. And these atomic clocks are in the field of quantum metrology to measure time. So these are some applications of quantum technology being used today. And of course, going down the future, we'll see more of this later on. Now, quantum computers, just to explain what is the difference between the different parts of quantum computers. So on the left here, I have the classical computer, and on the right here, I have the quantum computer. So the lowest level, you have bits, and then up here is where we have the programmer. You write program using C++, Java, Python, and you run some algorithm. Here on the right, let me go through with you. At the highest level is quantum algorithm. So this is where theories, quantum theories, or people who want to use it for, let's say, the application that I mentioned just now, create new chemicals, create new drugs. So people will be up here. Slightly lower, you can actually take all these libraries and you can check them. You go deeper in them, you get the quantum circuits. These quantum circuits, we'll see an example later, consists of a lot of gates here that I mentioned here. And these three, we call it quantum software. So you can code your algorithm using Python, using penny lane libraries. So there's different libraries, Qiskit library. Some of you might be aware and familiar with this, and all of that can be transpiled to a low-level quantum gate. I'll have some examples later. And then these quantum gates will then be sent to the hardware, and this hardware will generate some control signals. It could be microwaves, it could be optics. So it depends a lot on the system. It could be lasers. So for superconducting quantum computer, it's microwaves. So we'll go through that. Then next layer is the logical qubits. This is actually a collection of a few qubits to form one logical qubit. So that's what Google recently showed with below. So they used a physical qubit. I think it's 7 by 7. So they did a few 7 by 7, 5 by 5, and they showed that they used that amount of qubits to create a logical qubit. And why this is important is because all computers, classical and quantum, have errors. And having logical qubits will help to prevent these errors from making the calculation wrong, right? So what is a qubit and how do you build one? I'm going to talk about superconducting quantum computers. There's actually a lot of different kinds of quantum computers, but I am not doing those. So meaning that people who are doing photonic quantum computers, they won't be able to design superconducting. Similarly, I'm doing superconducting, I will be able to help with the photonic system, for example. So what we have here, this is a picture of the energy levels, so 0 to 1 to 2. And on the left here is a harmonic oscillator, and this have equidistance energy level. So the problem with this is that when you excite one, you put in some microwave, you bring it up to the next level. If you send it again, it just goes up and up and up, so it can or down or whichever. But it's uncontrollable, so you can't really use this for computing. You only want to use, for example, 0 and 1, and you only want to control between these two. So you don't want it to go up. So in order to do that, what we want is for them to not have the same energy levels. So from 0 go to 1, but 1 cannot go to 2. So imagine if you naik tangga, aras 1 dengan aras 2, 30 steps, aras 2 dengan aras 3, 20 steps. So jadi it's not really the same number of steps. So you can't go up to the second steps using the same energy. So it consists of this circuit. This is a capacitor, and this is a non-linear inductor. So this is what we call the Josephson junction. So this is how it looks like. But the important part is this middle part here. So imagine you take your finger with me, 2 fingers, and then you just sentuh atas here. And in between here, tempat yang dia bersentuh, there is an oxide layer. So aluminium, that's the material. Then tengah-tengah tu ada oxide layer, aluminium oxide. Then atas tu ada satu lagi aluminium. So these two and the aluminium oxide form the Josephson junction, and we can use this to combine with the capacitor to form a qubit. And this uses lithography as well, e-beam technology. So it's the semiconductor industry, the lithography and everything. So this is the fridge that I was talking about. And now here's a temperature. It's not that accurate, but it's just to give an idea of the different temperatures there. And at the top, from the room temperature, we use all these wires. And at the bottom here is where we have the quantum processor. So this is a quantum processor. And this is actually the holder here. And there's normally a cap or something. So the chip is actually in the middle. The side here are all these wirings to connect to the chip. So this is the quantum processor itself. So basically this is just a holder. So imagine if you have macam komputer biasa ada CPU, lepas tu dia ada packaging the actual CPU kat dalam, the silicon chip. So this is something like that. This is the chip inside that packaging. And this is our this is a 10 qubit chip. And if you see this one small circle, then you have this design, and this white spot here, that's the junction. So all the side here, because it's just a big surface, that is acting as the capacitor. So this capacitor plus the non-linear inductor, that forms the oscillator that I was mentioning just now. And why do you have so many of these, all these curves here and whatnot? So all of this is used to connect one qubit to another. So I'll show you what it means. So on the left here, we have 1 qubit. On the right here, we have another qubit. Then we have this red line here. This is another capacitor to couple. So we use the word couple to join them. 1 qubit to another. So this purple line here, this is how we send signals to our qubit. So this is our qubit here. So this is our purple line to send the signal, and this is what we call the readout line. So I'll explain a little bit more. So this is the qubit. So we send the signal here to control the state of the qubit. So we'll know what is the value, maybe it's at the 0 state or the state 1. And then to actually determine the state, we connect them to what we call the readout resonator. So this is a resonator connected to this blue line here. And when we send some signals here and then we read out here, we will know what is the state of the qubit. But these two is just for reading out. This green one, these two qubits will have different frequencies. So we will know that the states for each one. But to actually connect them, this red one here, this is where we use this. So this is the bus or the coupling resonator. So from one resonator, we connect to another, and this will couple them together. So that's the idea for two qubits paired together. You can actually increase them more. So like for now, the one I showed is the 10 qubit. So in between here are all the couplers. So to couple them. So these are the circles. So 1, 2, 3, 4, 5, 6, 7, 8 connected. So this is connected here. This is connected here, here, and here, right? And our design, the qubit is called a transmon. So there's actually different types of superconducting qubit. We set them to be about 5 gigahertz. So each qubit will have their own frequency, and we can control them by applying signals to that frequency. So this is a 8 qubit chip, and the junction size is about 200 nanometer. And we actually use either sapphire or high resistivity silicon. And the junction resistance is about 12 kilo ohm. So this is how it looks like. And then this is how it looks like with the cover on and the cable. So we have a few designs here and there. So this is a big one here. And there's a lot of chips in here. So this is one that is fabricated on the 4-inch wafer, and we will dice down into the individual chips. So that's how they look physically. So now just to see how do we control them. So this is where we are talking about the quantum circuit and the quantum gates. So the typical idea is to imagine them as a block sphere. This is what we call it. So for example, this red dot here is the state of the qubit. So let's say in Malaysia or Indonesia, we are at kat bumi ni, kita kat khatulistiwa, garisan khatulistiwa. And then kita nak pergi ke India katakan. So we have to fly up and left, for example, or we can fly direct. So there's a few ways to go to India. You have to fly to maybe Japan first, then go to India, or you have to fly to Thailand first, go to India. So the path is up to you. This is how it looks like by twisting, turning, rotating the 3 axes. So you can rotate it. So typically we will rotate between these two, alpha and theta. So those are considered the rotation or the quantum gate. So for example, from here, we want to go down. We just apply a 180 pulse, 180 degree pulse, and then we will rotate it from 0 to 1. And you can apply it again and it go back to 1. And this is called the NOT gate, because classically you have the NOT gate, you have input 0, you dapat 1, then you ada 1, you dapat 0. So that's the classical one. The quantum one, also the same, but it depends pada initial value. So kalau initial value dia pada kosong, then you dapat 1. But if the initial value is kat X here, then when you apply, then dia akan ada kat negative X. So this one we call plus and minus state. Or it can be, let's say my mouse here, and then you apply, then this one will be here on the other side. So it depends on the rotation axis. So X gate, they rotate kat sini. So for example, you have a Y gate, it will be something else, but it's 180 degrees and you have different kind of gates. So one of the most important gate is called the Hadamard gate. Yang ni classically kita tak ada Hadamard gate, cuma quantum saja, because you can have a superposition state. So superposition is the one that I was saying, 0 plus 1, something like that. So let's say your initial state is here. So you are actually rotating on this axis, and you are rotating also 180 degrees. So from here, this red line, this red line, you rotate to the X, you apply again, you will rotate back to 0. Yang ini kalau initial state dia ialah kosong. Kalau initial state dia 1, the rotation axis still stay the same. Then when you rotate, daripada 1 dia akan pergi ke negative X, and then you rotate again daripada negative X, dia akan pergi 1. So it's easy to imagine if it's 0 or 1. If it's somewhere else, then a little bit hard to imagine. So it will have to, what is. What I normally do is I take 2 pens, and then the pen, let me see. So this is what I did last time. You take 2 pens. You can try that now if you want. Maybe I stop sharing for a little while. So if you take 2 pen, and so this is your background. So one is your qubit state, and another pen is your rotation axis. And if you want to turn, you just swing around, and then that from up goes to down. Let me turn off my background. Okay, so yeah, from one, and you turn, then it goes to here. You can also do it like a Hadamard gate. So this is like this, and then when you turn, it goes to here, right? So you use 2 pens, you can play around, and you can get that. So yeah, that's just something nice to imagine. Right, coming back to my screen. Okay. So that's where classical and quantum is different. Classical tak boleh buat benda macam ni, quantum you can do all these kind of things. And there's actually a lot of gates. For example, the identity gate, the X rotation gate, the Z gate, Hadamard gate, control NOT gate, Toffoli, phase gate. So all of these are quantum gates that do not exist. Some of them, most of them, do not exist for the classical gates. So how do they look like? So you have this, what we call the quantum circuit, yang tadi saya explain tadi. So this is from Qiskit IBM. So this is just a simple circuit to produce 0 plus 1, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. This is 2 qubits, so you get 4 states. So you have a Hadamard here, and then this is called a control NOT, and then these are 2 measurement gates. So this is just a classical register, meaning you store the values here. So this is a simple circuit. Now on the right here is something slightly more difficult, and you can see all the different gates here. So this is a swap gate, I believe, or phase gate, and then these are X gate for a few degrees, and then you have some other gates here. So if you examine the gates, inside the gates for superconducting, you have all of these signals. So Q0 is the qubit. So this is qubit 0, qubit 1, qubit 2, 3, 4, until qubit 8. So there's 8 lines here. Kat sini cuma ada 2 lines, so there's only 2 qubits saja lah. So these 8 qubits, then the other tulis how long is the pulse, for example, 20 seconds, 45 nanoseconds, 20 nanoseconds, and so on and so forth. And this is the measurement one, which is normally a few 100 nanoseconds or tens of nanoseconds. So this is how it looks like. And how do we send this? How do we generate all of these waves? That is where we have the control hardware. So the control hardware, this is what we use here. So our group, I joined Singapore in 2018, and we have been working on a control system, and we are using an RF SOC system, and we built it, and we use this to generate microwave pulses. This I mentioned 5 gigahertz, so it generates 5 gigahertz from here. So this is an example of a square wave at 5 gigahertz. So this is a profile, and that's what it is. This is actually I don't remember the frequency, but well, that's not the idea here. But you get all these different profiles. So the Gaussian, this is called a drag pulse. So we create all of this using this hardware. And from our research since 2018 until I think last year, from there we have actually spin off and created a new company, and the company is called Axolotl. Yang ni sebenarnya nama binatang yang axolotl tu, the white color one. So nanti boleh cuba Google and tengok lah. So that's the icon for that animal there. And tapi spelling dia berbeza sikit, dia AXS, kita AQ sebab for quantum kan. So yeah, we have a startup, and this is the device that is being used in that is being piloted in the National Quantum Computing Hub in Singapore. So we have this device, right? And this device, we create the pulses that I showed you just now. So all of these wires is connected to the fridge behind here. So it goes all the way up, we send the pulses goes down, different temperature, it goes down, then it goes to the chip. And from here, we can get signals from the qubit, and this looks something like this. So it's quite beautiful. That's why I always show this picture. It looks like some art picture. So this is a Rabi chevron, and what is inside this fridge here? Ada apa kat dalam sini? So this is an example of it. So we tend to have like some pulse generation, so that's called a AWG, and then we have a ADC, which is used to read the signal. This is an older setup, but this is on the room temperature side, and then kat sini bawah sini is inside here lah. So we have some attenuators here, so it's just to reduce the power and to cool down the cables and whatnot. And then it goes to the sample, and then the sample goes back out. We have some amplifiers here and there, and then it goes to the room temperature device. And just to explain how we control it. So the idea is to apply a pulse. So for example, this is a square pulse of a certain duration. So let's say 20 nanoseconds yang tadi. So 20 nanoseconds, let's say it goes to here. And then if you apply a little bit longer, then you start, getting different states. And you actually can get this signal from the qubit. So this sine wave, we call it Rabi oscillation. So this is at one particular frequency, which is on resonance on the qubit, and then we actually get this. So if you want to do an X gate, for example, then you apply to here this duration. So kalau yang ni 20 nanosecond, then you apply dua kali ganda, which is here. So this is 40 nanoseconds. So to daripada kosong sampai ke satu lah. But if the initial state is somewhere else, doesn't matter. You still apply the same pulse, then they can rotate that state. And this is a real result. So this is a real signal that we get from the qubit. So this is the pi per 2 pulse, and this is the pi pulse. So kita tahu dia punya in fact the oscillation of the qubit lah. And this was obtained using this what we call a 3D qubit. So tadi punya 2D qubit, this is a 3D qubit. The difference is how we read out. This one is inside a 3D cavity. Yang tadi tu is on the plane lah. Okay, but that's not too important here. So this is the signal that we apply at the same frequency yang sama dengan qubit lah. And then if we change the frequency a little bit, what will happen is you will get a smaller signal. So this smaller signal will also be faster. So frequency dia akan naik, amplitude dia akan kurang. So this is actually what is happening is, if you see the picture here, yang ni pusing kat sini. So it's going up and down, 01, north, south, north, south, north, south. But if the next one, the pusingan is just kosong, and it's pusing like macam Hadamard gate tadi. So if you know this detail, you can actually create a Hadamard gate because you know what is the frequency and how long to apply to actually get this kind of signal. So Rabi oscillation is one of the calibration method for you to actually find out how long is a pi pulse, how long is a pi per 2 pulse, or the duration yang tadi 20 nanosecond, 40 nanosecond. So if you change the frequencies here, what you will get is you will get this Rabi chevron. So gambar yang cantik tadi lah. So this is the general idea. So that's on the hardware. Jadi my expertise is on that. To build the qubit itself, we have a different group. Tadi Dr. Rangga dia part of the group yang subgroup yang buat the qubits lah. Saya subgroup yang buat the control system. So above those layers is where people are building algorithms. So this was the one that I was saying tadi. So you have like IBM, Google, they have their Circuit, Penillion by Xanadu. So these are all the higher levels libraries or libraries to control. And then from these libraries, you can get what we call the open chasm. And open chasm, I will show you later on, is the low-level assembly language, quantum assembly language that is sent to the hardware. So the hardware, as long as dia terima this open chasm language, dia akan tahu what to apply. So that means your hardware mungkin optical system pun boleh, mungkin laser system pun boleh, mungkin microwave pun boleh, asalkan the open chasm supports open chasm, then you can use it. So different quantum processors have different properties. So What I didn't explain here is the T1 and T2 time. But let's see if I have enough of time after this, maybe I can go into that. Tapi ini agak technical sikit lah. Then QPU circuit is macam tadi kita susun 8 ke 10 ke macam mana kita susun dia punya circuit. That actually matters. Then which gate do we support? So macam tadi ada yang support cross resonant gate, ada yang guna I swap gate. So different gates for different purposes. And sometimes you have these values, quantum value, volume, circuit depth, circuit width, or length. So depth is, kalau macam tadi, I'll just show here. So depth is here, I believe, going down. So more depth means more qubits. Length, the circuit length is more gates. Okay, so how much gates you can support is also important, and going down is how many qubits. The quantum volume, I am not so familiar with how to use that. So yeah, maybe if you are interested, you can read more about it. And this is open assembly language, quantum open QCASM. So this is like all the short codes that is used to generate the gates. So this is HQ0, so Hadamard on qubit 0, control not on the control and target qubit. So this is this. I apologize if you hear a bit of sound. There's some renovation going on near my building. Right. So this is a basic idea of a quantum circuit, and you can actually use quantum computers right now. So this is a bit of an older picture. So IBM, you can actually go to IBM Q, their website, and you can actually pilih the quantum computer there, and they will tell you what is the number of qubits, what is this quantum volume, what's the status. And if you open here, you will see this kind of layout. So I'll explain a little bit to you what do you see here. So jobs, that one, your queue, basically this is the name of the qubit. Basics gate, so this is the gates that I was saying you support upper. So CX is control X, identity gate, rotation sec gate. This is a swap, I think. This is X gate, and then there are actually some errors when you're controlling them because it's not a good, a perfect control. That was what I was saying. Tadi kita perlukan logical qubits. So this is because of all the errors lah. So this is an average C0 gate error. So C0 means a 2-qubit gate errors. So this is how much error they have. This is the readout error. T1 and T2, I didn't explain about that, but it's basically how long you can keep information in your qubit. So that's why bayangkan kalau kita ada pen drive, kita simpan data dalam tu. Lepas 7 hari data hilang. So that's not so good, right? So that's basically T1 time. So it tells you T1 and T2. So it tells you how long you can keep information in the qubit before the information is lost. So this is the average. And if you see this one, you have these beautiful colors, right? These colors shows the minimum and the maximum. So it shows the frequency. So tadi yang saya kata setiap qubit ada different frequencies, for example. So this one shows the frequencies of the qubit. And you can actually change this drop-down menu. You need still picture, so I cannot do that. So you can see the error of like here, the error, how much is the error. So kalau minimum tu yang best lah. Yang purple, bright purple ni, yang ni teruk lah. So this one is like, yang ni teruk, yang ni teruk, yang ni teruk, yang ni teruk. So that means if you use this, dia lain sikit dengan classical. Classical kalau guna, you tak kisah macam mana dia sambung. But in a quantum computer, sambungan dia agak penting lah. And kalau kebetulan there's this qubit here yang teruk, then your data bila you process, dia akan jadi kurang tepat sebab ada satu qubit kat sini yang teruk. So if you choose a quantum computer, semua orang mungkin dia akan tengok, oh Q ini panjang, when you're wondering why. Most likely because that quantum computer is better than the other one lah. So yeah, you can actually see that things. These are the smaller ones. So yang ni rasanya dah tak ada dah. 5 qubit dengan the last time I checked, semua tak ada. Yang paling minimum is 120 something qubit. Tapi kena bayar lah kalau nak guna. That one I don't have money to pay that. Plus I'm actually on the hardware side. Saya tak guna untuk theory lah. But there are people using this. So this a few examples of quantum algorithm. So Shor's algorithm yang ni guna untuk factorization. Gauss-Sum is also factorization. Grover's search algorithm is a searching algorithm. These are all to find the lower energy level for like VQE. Then you have quantum machine learning, quantum classification. So these are typically theories that are doing lah. So saya tak mahir sangat dalam sini. But here in UTM, saya pujuk rakan saya untuk guna quantum computer. Dia bukan bidang quantum computer lah, he's a theorist. But then I tell him, come on, try out something. And we try to use VQE for his nuclear pairing calculations. So this is pairing calculations on a helium-6. So this is a quantum simulator, bukan real quantum computer, ini sekadar gambar saja. So it uses two parts, the quantum computer and the classical. So yang bahagian quantum dia akan kira dalam quantum computer, tapi dia masih ada optimization. So the optimization is done on the classical computer, and this is SPSA, is a classical algorithm lah. So this is what we do now. Tapi mungkin masa depan semua boleh dibuat dalam quantum computer, tak perlu buat this. Tapi untuk masa terdekat, this is the approach. And that is why people are putting quantum computers gabung dengan HPC, letak kat data center, so that kita boleh guna this tool to calculate at the same time. Not at the same time, tapi they work together lah. So for our calculations, we use what we call fake Guadalupe. I think there was one quantum computer nama dia Jakarta dulu, the IBM. But all of this is just nama lah. The physical location bukan kat Guadalupe, bukan kat Jakarta. I think Malaysia tak ada. So we use this fake quantum computer, fake Guadalupe. It's a simulator. Lepas tu kita modify the properties, and kita panggil dia fake Johor sebab kat Malaysia tak ada lagi nama dalam IBM Q, jadi kita panggil fake Johor lah. And then we did some calculation there. And what we did was we changed the coherent times of the qubit, and then we changed the error. So this is T1, T2. Lepas tu kita buat calculations on helium-6 lah. And what we see is where basically we have this map to say what kind of specifications yang bagus untuk kiraan. It's just for this calculation, because kalau buat calculation lain, then mungkin akan dapat graph yang berbeza lah. And also if you use a different quantum computer, mungkin akan dapat graph yang berbeza. So this green line here is a state vector calculation. So this is the target. Jadi yang hijau ni adalah yang accurate result, dengan yang merah ni semua yang salah lah. So of course the best is masa yang error yang sekecil yang boleh, and then the coherence time yang paling panjang lah. This is of course the best lah, without a doubt. Tapi kat sini semua masih error dia is still acceptable for our calculations lah. And just to show you the quantum ecosystem, yang ni bukan saya yang buat, yang ni daripada Quantum Insider. So you have different value chain of the quantum ecosystem. So kita ada yang users, Merck, BMW, OTI, Airbus, for material science, finance, life sciences, other applications, users, and then there's also applications here. Then softwares. So I think there's Fujitsu here, AWS, and these are the quantum computers, the QPU, the quantum hardwares. So superconducting, other all these players here, trapped ions, neutral atoms, semiconductor. So Intel is trying on semiconductor, photonic systems, and then this is NV Center from Australia, NV Diamond, electrons on helium. This one I'm not too sure yet. I need to read up a little bit more on that. And these are all the hardwares lah. So for example, cryogenics, microwave components is actually not here, but you have some here. For example, Keysight. Then the control system, for example, Let me try to find a few. Where are you? Quantum machines, Delft circuits. These are Q blocks. Yeah, this is the control system. So this is what is used to control. LNF is amplifier, microwave amplifier dalam dilution refrigerator, dalam cryogenic. So this is some of the players around there. And just to introduce what our startup is doing. So we are basically just a history of what we are doing. So to yang saya tadi saya mentioned, we started up in 2018-19, and then the first product is the first generation is Icarus Q, and then we started out with Kronos Q, and that is the one that is piloted in the National Quantum Computing Hub in Singapore, and we are now going towards AI. So that's how it looks like, and yeah, so it's designed to be scalable. You can connect other systems. So kalau katakan guna 20 qubits sekarang, dan lain kali bila upgrade untuk 40 qubits, then just need to tambah saja. If the hardware is the same, but katakan the firmware inside the outdated, we can actually just flash it and then upgrade to a latest firmware. So the hardware remains the same. And that's where we are, Kronos Q. For the company, and kita pun akan buat our own quantum computing processor, and by 2026 kita akan fokus kepada quantum AI lah. So that is where we will have on the same control system AI acceleration, and we will be connecting to HPCs to macam tadi saya kata, to do the calculations faster while waiting for the full what we call the quantum advantage. Right. So I think that's all for me. Let me see the time. Oh, okay. Yeah, I'm somewhat there, I think. Yes. Right. So if there's any questions, let me see the chat.
Okay. Thank you. Yep.
Yep.
For your interesting presentation today.
Thank you very much.
For the audience, today talk give us valuable insights and how to control the qubit using quantum gate, and also Dr. Yap also present about the recent research on variational quantum eigensolvers, especially for nuclear pairing calculations. And I think this example can making us this information, very important information for both beginner and also those interested in advanced quantum application, especially connected with the quantum company, because Yap and also the fellows from NUS and also NTU has already started to build the company. And currently we have 30 minutes for our question and also answer sessions. So to all participants, if you have questions, you can either post your question in the Zoom chat or raise your hand if you would like to ask your question directly to the speaker. So let me read the question in the Zoom chat. The first question is come from Asus. The question is that quantum computer consists of the quantum size transistor or atom?
Right. So the quantum computer consists of a lot of qubits. So each qubit looks like this. So we don't really call them transistors because transistors is something which is more for the classical computers. So we use this kind of Josephson junction combined with this capacitor. So inductor and capacitor. So this becomes the qubit, and by copying this and pasting all over, then you get more qubits. So it's an artificial atom. So this becomes an artificial atom. So kalau tak guna yang ni, boleh guna macam contoh awal-awal dulu saya buat electron spins. So that is dalam molekul tu ada satu electron, then kita guna electron tu sebagai qubit. That is also possible. So in terms of atom or molecule, that is on that side lah. Kalau superconducting, this is what is. So dia ikut jenis quantum computer.
Yes, thank you. Yep, I think you mentioned about transmon also, right?
Yes. So this is the name of this superconducting qubit. So there's fluxonium, transmon. Tapi itu agak detail lah. So yeah.
Yes, for this case, is there any reason for you to focus using transmon?
Not really. We are actually trying both as well, fluxonium and transmon. So different, both of them have different advantages and disadvantages. But so happen for us, it's easier for us to use transmon at the moment. But yeah, we are actually trying both, and then we are trying to see which one is better for our case.
Better for your kids. Can I ask about the qubit lifetime for this case? In case, have you done for these two cases?
Our fluxonium is typically shorter, if I remember.
Oh, shorter.
Our fluxonium is shorter. I can't really say. This is on kerja yang kita buat kat CQT. I can't really say how much is the lifetime until we get some publication out, but so far we are like equal to some of the companies out there. I mean the research in the group bukan syarikat lah. Syarikat kita belum ada qubit lagi. Kita akan go into that.
Okay, thank you so much. For your answer. And then the second question is come from Muhammad Taufiki. And the question is the current quantum computer already able to perform a post-measurement unitary operation?
So the measurement unitary, it's not unitary, I think, because when you perform the measurement, you collapse the qubit. So kiranya maklumat tu akan fall to either 0 or 1. So you won't be able to use the qubit again. So macam you reset lah. So kalau you format dalam komputer, you format dan dapat balik, you tak boleh dapat balik. So we actually use the readout, the measurement, and then lepas guna tu basically dia akan reset kepada kosong, lepas tu have to program balik lah.
Okay, and for the next question is also from the Asus. Asus is the one that asking for the first questions, and he asking why need different temperature at each level.
Oh, okay, that's the fridge. So this one. So it's not purposely that, I mean, we so if we want to start from room temperature and then terus kepada millikelvin, maybe in the future kalau ada a new fridge, but the current one it cools down step by step because the system at each stage have a different mechanism to cool down. So daripada 50 Kelvin dengan 3 Kelvin sebenarnya ada dua alat berbeza untuk sampai suhu kat situ lah. So the first one, dia cool down hanya boleh sampai 50 Kelvin. Then dia akan turun kepada the second stage, that bahagian memang akan sampai 3 Kelvin. So it is not dengan sengaja, tetapi it's kesan daripada peralatan tersebut. So then bawah sikit lagi, the 3.9 Kelvin, that is, I think, because of where the helium-3 and helium-4 it collects or something. And then kat bawah sekali tu, the lowest temperature is where we have this special mixture dan ada dilution kat situ lah. So dilution here is helium-3 being diluted inside there. So that's why it's called helium-3, helium-4 dilution. So yeah, that's a bit complicated. But so there are actually people who are actually doing this kind of research, low temperature physics, nak bina alat-alat macam ni. So the idea is that you have, when you cool down to this temperature below liquid, below 4.2 Kelvin, helium-4 will become liquid. So helium-3 saja yang sebenarnya pusing within the system. Helium-4 akan kekal dalam liquid within here lah. So bila helium-4 ada liquid tu, ada bahagian yang kaya dengan helium-3, ada bahagian yang poor with helium-3. So these two boundaries lah. So macam air dengan minyak. So when the helium-3 cross this boundary area, this is the process of dilution, pencairan. it will collect energy from the surrounding. So tu yang dia sampai kepada millikelvin. So the stages is important, and not purposely, but it's because of the equipment, how it functions.
Okay, thank you. Yep. So this question is actually come from Asus. Asus is Azam. His name is Azam from Mahasa University.
Okay.
So
Nice to meet you,
also Azam, oh yeah, from Mahasa University. And then the next question is from Dr. Hamzah Fauzi from our research center. Thank you, Dr. Yap, for the presentations. The question is there any open platform out there for superconducting qubit quantum hardware or control?
So platform, yes, there is. So there's so macam tadi yang Qiskit, those are languages, APIs, or those are also actually open per se. But if you want to have platforms for the hardware, the not hardware as in the quantum, the processor, tapi dia punya control system, I think that will be Kibo. So Kibo is a open source kind of international effort to build this control system, and then it's basically a different library compared to like Qiskit. And from what I heard, I mean, we are also using one of our, Paul is also a PhD student, and he's part of the lab and also the company. And some of his work when as a student was also to help with the keyboard library. So that's some open platform for you to control the quantum superconducting qubits.
Okay. The next question is come from Gracia Ra. May I know ongoing research on quantum algorithm, specifically applied on CHT quantum hardware?
So there are two quantum computers which our group is related on to. So one is the NQCH. That one is the National Quantum Computing Hub that is open to the local researchers, and maybe in the future also to the regional researchers. And another one which is in our CQT lab in NTU. So at the moment, we did some Gauss. Historically, we did some Gauss sum algorithm, but not too high level. Like we didn't do Shaw's factorization or VQE. We haven't done anything of that level yet. We are just doing basic demonstration. So far, there are other groups working on quantum algorithm in CQT. Many groups actually in quantum machine learning also, but I believe they are using other quantum hardwares, not the one in CQT. At least not the one in our group.
Okay, thank you very much. And we have a question again from Rafika Ramawati from our research center. In terms of the gate fidelity and error rates, what is currently limiting the precision of the quantum operation?
There's quite a few things that is limiting the fidelity, or basically we have errors, right? And that is something that everybody is working on. So the fidelity is a combination of everything. The control system, the qubit T1, T2 lifetime, the uplink to the environment, the noise from the control system, it's everything. So to reach high fidelities or low error, people are trying to work on that. That is where one of the bottlenecks, because once we reach 2 qubit gates, about 99.9%, I think recently, last year, IQM announced that they reached that value, 99.9. And I think I heard that Google also actually did reach 99.9 in one of their older papers, but it's only for specific qubits. So the challenge now is to apply 99.9 to all of the qubits. So it's not that easy actually. So there's a lot of errors that we need to work on to make it to have high fidelities above 99%. So as I mentioned just now, it could be the pulses, it could be the leakage, so 0 to 1. So there's actually some frequency components that might cause it to excite to 1 to 2. So that's bad as well. And then maybe some thermal noise, maybe some spurious noise, and then the T1, T2 lifetime, which is too short, that can also contribute to the gate fidelity.
Okay, thank you. Yep. For these cases, yep, it's possible to identify the noise come from. I mean, from the simulation, we can set up, for example, if we have depolarizing noise, and then we can set up in the Pauli X, Y, Z, and also amplitude damping, we can set up also. But in the real system, it's possible to identify what is the most dominant noise for certain calculation. I don't know exactly.
Yes, that is something that we are actually investigating as well, because it's not just noise. So some effects that previously I was studying is, for example, we send square wave. Square is perfectly, you have this discontinuity. So in a real system, you cannot have these sharp edges. So there will be some rising edge and falling edges. And when we send a square pulse, rectangular pulse, when it goes through the system, it might deform. You might not have the same square shape. And if let's say we send 20 nanoseconds for a pi per 2, tapi nilai sebenarnya mungkin 20.12. So you ada error sikit ke sana. And then frequency mungkin bukan 5.11 tapi 5.123, something like that. So all of these small differences adding errors. But yeah, we can definitely simulate that. So some things, but that's the thing. Fidelity is error daripada semua. Biasanya kalau kita buat simulation, kita cuba satu-satu, and it's hard to say now which one is the major contribution. Tapi T1 and T2 memang kalau pendek sangat, the fidelity will be low. So that is definitely one thing. So increasing the T1, T2 can help. Then kemudian kita kena tackle satu-satu sampai dapat 99.9.
Okay, I think also this is complicated, I think,
Yes,
because
yes.
the errors not come from qubit, also from the environment and also material itself, right?
Yes,
So
exactly.
we go to the next questions from Azam again, from Hasa University. Why send an electric pulse, not continuous electric, to operate the system? So
Oh,
why
okay.
so why we don't use
Continuous.
electric to operate the system?
Yeah. So continuous microwaves, if we use that, kita tak boleh control nak stop kat 1 ke atau 0 ke. So actually if dalam spectroscopy kita biasa guna continuous saja sebab you only get just the signal. Tapi kalau nak guna untuk quantum computation, then typically kita akan guna pulse lah. So for example tadi yang I show the X gate ke Hadamard gate, so we have only to send 20 nanoseconds. Dia kena stop kat 20. Kalau tak nanti the gate akan jadi something else lah. So if you send continuous for 1 second, you won't be actually controlling it. It's just getting some signal, right? And you might actually saturate it as well. So this is normally macam untuk NMR spectroscopy. NMR spectroscopy pun guna pulse. Electron paramagnetic resonance, EPR or ESR, electron spin resonance yang chemistry biasa guna, that one biasa masih sekarang continuous wave. Tapi ada orang pun dah mula guna pulse lah. So spectroscopy pun dah mula guna pulse actually.
Okay, thank you. Yep. And the next question is from our KOLOKIUM admin today. he is asked about your PKA study. So the question is, in your work related to the nuclear structure calculation, what makes your algorithm don't need error correction?
Oh,
So why you don't need the error correction for your cases?
It's not that we don't need,
Ah,
tapi error correction yang macam Google tunjukkan dia ada quantum error correction, QEC,
surface code.
like those,
Okay.
those surface code, topological code, different kinds of QEC codes. That one is implemented on a low level. Dia bukan kat bahagian algorithm. So katakan kita nak buat X gate, macam gambar tadi saya tunjuk satu X. But logical X gate is something else entirely different. Dia tak sama dengan kat sini. So it's not something that you can do at the algorithm level. So that is why tadi gambar ni is this layer, logical kat bawah, algorithm kat atas. Jadi kalau kat atas level macam VQE, kita tak nampak dia punya error correction, quantum error correction kat bawah. So we cannot actually affect that. And in our case, kita tak guna bukan sebab kita tak nak guna, tapi sebab kita tak boleh control. Dan yang kedua ialah we actually want to see the effect of the errors. Kalau ada quantum error correction, then this graph dah tak perlu lagi dah. Then it will be accurate already. It's supposed to be accurate lah. So sebenarnya kalau ada kita lagi gembira lah sebab kita boleh terus guna untuk calculation. Tapi there is error, so that's why we have to we just study what kind of errors that we can work with.
Okay, because you saw the picture is there are a lot of red. The red one is so many error in there, and basically if you using quantum simulators for this case, it's possible to mimic the real system. Like for example, you just introduce not like artificial the polarizing channel or amplitude damping for this case, and then you just increase the noise level, and then you just extrapolate. We call as
zero noise extrapolation.
Zero noise extrapolation.
Yes, Z and E. Yes, that's one.
So do you try also for these cases? No? To see the this error effect is because the red one is very big, right? The composition compared with the green one.
Yeah. So zero noise extrapolation. Let me try to draw. So this is our noise. Oh, merah dengan merah tak nampak. Okay. So this is our noise here. So basically, zero noise noise will be equal to.
You share screen, no? Yep. You want to share screen or no?
Am I sharing? Can you see?
Not yet.
Okay. Let me stop.
Okay. Thank you. Oh, you basically also you did the calculation for zero noise extrapolation.
No, we didn't do. But we actually changed the noise kat bawah sini.
Oh, I see. Okay.
So technically, if you want to go zero noise is this direction lah, Z and E dia ke arah sini kan, dia tambah kurangkan noise, then we know what is pada zero noise.
Okay, for this case, what kind of the noise? You just using one kind of noise, or for example, you compare.
We all the gates that we apply, we increase the noise for all. So single gate, 2 qubit gates, everything.
So it's more like the polarizing channel, I think.
Yes. Yep.
Okay, because polarization is just probability Pauli XY also zero.
Yep. So we change all of that, including the 2 qubit gates as well, the C nodes, CZX. Yeah.
Okay, thank you so much. Yep, this is very interesting study.
Thank you.
And again, there is question from Azam.
Sure.
Why there is too many quantum algorithm? Which one is more accurate and perform well when you do calculation?
So basically everybody is trying to come up with different algorithms to see which one works best. So macam classical algorithm pun ada banyak. So like let's say Fourier transform. So you have Fourier transform, you have Z transform, you have Laplace transform, different kind of transformation, wavelet transformation. So yeah, different people do different things. Same for quantum. Different people coming up with different algorithms, and some of them have specific purposes. Which one is better? Honestly, I don't know, because saya bukan quantum theorist lah, and to be able to answer that, it will be someone who actually use different kind of algorithms. Tapi kalau algorithm berbeza, mungkin dia ada tujuan berbeza. So I don't know. I don't think it's as simple as comparing, for example, Fourier transform nak compare dengan Laplace in DFT masih okay because they have the same purpose. Tapi kalau nak Fourier transform nak compare dengan Monte Carlo, so these are two different purposes. So agak suka untuk bandingkan lah.
Okay, thank you. Yep, it depends on the objective of your study or research. For example, if you want to see the ground state, some ground state calculation using, you can use a variational quantum eigensolver.
Yes,
If
exactly.
you want to use another cases, maybe you can using cubo problem.
Yes, exactly.
Okay, and then the next question is from Solihin. For example, what happen if all level have the same temperatures? For example, 3 Kelvin. What factors should be considered when choosing the material for each level? So the trade-off between temperature and also material in the layer.
Oh, okay. So where was it? I think never mind. Let's use this one. Okay, so so the temperature here is important because just now yang aluminium oxide dengan aluminium, the material aluminium, it must be superconducting. And for aluminium to be superconducting, it must be below, I forgot, is it 300 millikelvin? So it has to be below a few millikelvins, few hundred or something, below 800 thing. So that is the first requirement. So it has to be superconductive. So if it's at 3 Kelvin, then you cannot use it as a qubit anymore. Second requirement, so we have the energy to excite, which is 5 gigahertz. So this 5 gigahertz, you can actually check the thermal excitation corresponding to the temperature. So kalau a hot body will have some frequency, and for you to use 5 gigahertz or 8 gigahertz, it has to be below 100 millikelvin. So that means nak kena turun ke temperature tu lah. Otherwise, another option is maybe using higher frequencies. So there are some people trying to go to hundreds of gigahertz perhaps. But yeah, that's the reason why we need millikelvin is two reasons: the energy separation and also to be superconductive. Kalau suhu dia panas, katakan superconductive tapi masih panas, then the qubit, maybe the lifetime will be shorter, the T1 T2 time might be shorter, and then maybe you might get random excitation, tak control pun tiba-tiba from 0 become 1. So that's bad lah. So if everything is 3 Kelvin, tutup kedai, tak payah buat experiment. So yeah, we actually need to go down lower. And why we use aluminium? So I think there's other people, they are investigating other materials as well. But in our group, we are trying out with aluminium first. So yeah, there's actually people trying out different materials. The main motivation is to try out different materials and see which one can give you the most stable or good quality qubit.
Okay, thank you, Yap, for the answer. And this is the last question from Chat. So the question is from Ira. I want to clarify. So this pulse-based quantum control is not universal, but depend on the hardware. Would you like to explain more basic concept of the control else than superconducting hardware?
Oh, true. So different quantum computers will have different control system. Superconducting uses microwave. last time when I was in Japan, I used electron spin, which is also microwave. So that's why I can move from electron spin to superconducting. NMR uses radio frequency, so technically same family there. But if you go to photonic system, then you start using lasers, photonic chips. If you are going to trap ions, you use lasers. If you are going to NV centers, it's a combination of laser and microwave. And then if you are going to semiconductor, it's microwaves. So different systems have different methods of controlling. So it's not universal. That said, I don't have expertise in other systems. So if you ask me to build a photonic quantum computer, memang tak boleh. But what I can say is I know superficially, very surface level, conceptually how they work. So for photonics, normally they have a beam splitter, and this beam splitter will create so like you have the Mach-Zehnder interferometer, and that becomes like you create an entangle superposition of vacuum state and single photon state, and you can actually use that as your qubit. Some people are using the polarization of the photonic or the photons, so the right circular polarization and the left circular polarization. So they use a different lenses and stuff like that, obviously. So yeah, it really depends on what kind of systems. So if you are using trap ions, you will use lasers, and I believe you will I suspect I might be wrong. You actually shine the laser to control the state. So if there's somebody here who knows about that, maybe you can share also, because I don't really know. NV centers, they use microwaves, so it's still the same, but they use laser to bring it to zero. So they will bring all of it to zero, and then that's why they don't use low temperatures. So they just use laser to reset everything to zero. Then daripada situ they apply microwaves, for example. But yeah, true. Other systems uses different methods, and unfortunately, I'm not a good person to comment on that.
Okay, yeah, thank you so much.
Um,
And we have actually 3 minutes left, and maybe I will ask a question.
Sure.
Yes, a little bit about your variational quantum eigensolver for nuclear pairing calculations. In that case, you are using the classical part is SPSA optimization, right? And in this case, can you elaborate more? Did you also try some benchmark in comparison between, for example, for SPSA, and then for the other classical optimizers? And then that one, and then the second one is also about what is your strategy to choose the specific ANSAS design for this case? ANSAS,
okay.
because this ANSAS is actually affected if we, for example, in your case, you are using the circuit deep is around quantum secret is 250 bit, right? So it's mean that the ANSAS is very important also in this case, right? So I mean that do you have any strategy to choose, or you just directly use, for example, hardware efficiency ANSAS, or did you try some ANSAS and try to compare with different classical optimizer parts?
Okay. So I'll start with the optimizer first. So we are using Qiskit for that, and there's 3 or 4 different optimizers as well. So SPSA is one of it, and then I forgot the names. There's 2 more optimizers. We did try to compare them, but it's not so straightforward. And if you just use them off the library without tweaking the optimization parameters, that's not so good as well, because we noticed for some initial states, some parameters will perform better, parameters will not be so good. So to answer your question, yes, we did try a few. For this particular work, we maintain with SPSA, but at the same time, an extension of this work is to actually try out different optimizers. I think our students who actually work on this have also so there were two things that we were investigating. One is the optimizer, and another is there's one. Okay, oh yes, I remember now. So SPSA, why we chose with this was we wanted to stop the calculation as fast as possible, meaning that let's say we do 200 iteration or 1000 iteration, and then the results have already reached a steady state at the front. So maybe after 50 iterations, then that is already same until 200. So we came up with sort of like a fitting algorithm to actually check, and if it's reaches that value, we terminate the calculation, so we can stop it early. So that's why we use SPSA. So SPSA goes up to, maybe we set the full maximum iteration is 200, but we can stop it early, so we can save time. There was another optimizer. It works, but we have to go through the entire 200. So it will like jump around, and then it will choose the lowest out of that or something like that. So we can't use our method to cut short. So you still need to wait for it to finish the iteration. And then for the ansatz, I'm not the best person to answer this, honestly. That I'll need to refer to my colleague. He's the quantum theorist in this. But I think, yes, I do recall we were discussing something of the ansatz, but I'm not confident I can answer your question on that.
Okay. Yep. Thank you so much for your answers. So I think the time is up. And again, thanks for your amazing presentation. Yep.
No worries. I apologize if it's too technical.
No, I think we thank you so much for your sharing your time with us today. And we do really appreciate your participation as a speaker today. And I would like also thank you to all the participants for joining us today. And we greatly appreciate your participations. And we look forward to seeing you again at our next Brain Quantum Physics Colloquium. And have a great day, everyone. See you next time.
Thank you very much for inviting me as well.
Okay, thank you so much.
Thank you very much.
See you.
Thank you, everyone. See you. Bye-bye.
Bye.
Thank you.